Hi everyone, this is Dr. Hopkins with our next video in our series. In this one we're going to define acids and bases. So acid-base is a really important concept in chemistry. You'll encounter in organic chemistry. If you go anywhere in terms of reactivity, you'll use the terms acids and bases. And just because it's so important, there are multiple definitions. And so we're most likely to deal with, and at least in 106, two of them. The first is the Lewis concept, and that's the idea that an acid is an electron pair acceptor, and a base is an electron pair donor. But what we're going to focus on in this part of the class is more like Bronsted-Lowry acids and bases. And a Bronsted-Lowry acid is a proton donor. Okay, so a proton is H+, because remember hydrogen starts with one proton and one electron, and so if you write H+, it's just a proton. Bronsted-Lowry base is a proton acceptor. And basically in any of these definitions, if something's an acid, you must have a corresponding base. Nothing can act like an acid, can't donate a proton to nothing. Okay, so it has to have a base. So how do you know if you have an acid? How do you know if you have a Bronsted-Lowry acid? And, the answer to that is it's not really always that easy. There are some clues in the way we represent the structures themselves. So when we write out the formula, if you have lots of H's, not all of the H's in a formula or the protons in the formula are acidic, especially in water. But oftentimes we will write them with the acidic H in the beginning of the structure. So here I give examples of HCl, HBr, H2SO4. And when it's not written at the beginning of the structure, so you're like this example, acetic acid. Now, if you have the name usually gives it away. Notice the H, and I've got in red, the acidic H is at the end of this. And that's because the structure, if we were to draw the line angle structure or the Lewis structure, but the line angle structure is more formative, because you'll notice we have three other H's and we don't draw them in this line angle structure. And that's important because in the line angle, any H that we don't draw in the line angle structure is not going to be acidic. And actually, it's one of the reasons why we actually write the H's on O, N, S, any other than carbon atoms. So what about a base? How can you identify a base? And actually, in this case, it's a little trickier because you have to know reactivity. You have to know that it'll accept the proton because it doesn't obviously have, this place. It doesn't obviously have a proton like an acid does. So you have to kind of look at the structure. And generally, if you have a lone pair like nitrogen, so nitrogen typically has 3 bonds and a lone pair, that lone pair is where it accepts a proton. So we have like ammonia and NH2CH3. The other example are OH-, so hydroxide ions. Hydroxide ions are bases. So anything that is a soluble hydroxide, so that you'll get OH- in water, is a base. So let's write these, let's look at how they behave. So we have hydrochloric acid, the H in red is our proton that we're going to donate. We're going to add it to water. Okay, in that case, remember we said originally can't be an acid without a base, so water's got to act like a base, all right, because we know the hydrochloric acid is an acid. And so that proton will attach to the H2O, as was shown, or we'll write it as H3O+. Now, here's an important point. We use H+ and H3O+ interchangeably in chemistry. So one is just a hydrated proton. One's written straight out as a proton. In general, they represent the same thing. So let's write the reaction. So we got our HCl plus H2O. We have an equilibrium written here. We haven't decided whether it's an equilibrium or an arrow. And we have H3O+, which comes from our water accepting the proton. And then we have Cl-, which is after we've donated the proton, we're left with a chloride ion. So in this case, HCl is our acid and H2O is our base, okay, on the reactant side. And on the product side, we're forming Cl-, which is what we call the conjugate base of HCl. So after the acid donates its proton, it ends up as the conjugate base. And so that's what we end up on that side. And then since H2O is the base, we need to have the conjugate acid of H2O. So that's after it's accepted a proton, it's H3O plus. So any acid-base reaction is always acid plus base gives you conjugate acid plus conjugate base, which means that these acid conjugate base and base conjugate acid pairings are very important to learn, because if you learn those, you can then you can predict and write the products of any acid-base reaction. So let's do the same thing for a base. And we have ammonia, one of the ones we had example. We're going to add it to water. So ammonia is going to act like a base. So water has to act like an acid. So we get OH minus and NH4 plus. So if we were to put that in the language we used last, we had NH3 as the base, NH4 plus is our conjugate acid. And then H2O is acting like an acid, and so OH minus is its conjugate base. It's important to remember, so NH3, NH4 plus, those pairs are involved no matter whether you're reacting with water or some other acid. It doesn't really matter. You will always go from NH3 to NH4 plus. But you'll notice in these last two slides that water's acted like both an acid and a base. So what if we put water with water? We get the auto-ionization of water. So you get H3O plus, the conjugate acid of H2O as a base, and OH minus, which is the conjugate base of H2O as an acid. So you'll always have H3O plus ions and OH minus ions in water. It's just you don't have very many of them, as we'll see later on. So some acids and bases are what we call strong. What that means is that they completely dissociate, so 100% in water. And so they're a strong electrolyte, which we'll get to in later on in the course. That means they completely dissociate. So if we had, say, HCl, you get your HCl, you put it in water, and you'll instantly get Cl minus and H plus, and that's it. No more HCl is left. And fortunately, the number of strong acids, or maybe unfortunately, I don't know, of strong acids and strong bases is finite. And so if we look at our strong acids, we have 7 of them here. We have HCl, HBr, and HI, HClO4, HClO3, HNO3, and H2SO4. Now that last one, notice it has 2 protons. Only the first proton is strong. The second proton is not strong. It's not 100%. The strong bases, the list is really simple. It's all your soluble hydroxides. So hydroxides are your strong bases. So basically any of your first column hydroxide salts, so lithium, sodium hydroxide, any of your larger second column hydroxides, the ones that are soluble, are also strong bases. You need to learn this list. I don't ask you to memorize too many things, but this list of strong acids and strong bases, if you memorize it, you'll save yourself a lot of trouble. So when you have these strong acids and strong bases, we don't have to write them the same way we wrote earlier. We don't have to usually represent the H2O. So HCl, for example, completely dissociates into H plus and Cl minus. And you'll notice we have written it as an arrow, and that basically means we have 100% dissociation of HCl into H plus and Cl minus. We have our acid, we have our conjugate base, and then H plus is coming from the HCl, same thing as H3O plus. H2SO4, as I said before, only the first proton is strong, but once again we write this is 100%, and so this is our acid. And then the conjugate base that we need to know is HSO4, and then there's a H plus. So we don't have to write it out as H2SO4 plus H2O. You can, but it's not necessary to represent what's happening with a strong acid, strong base. So it's really important that you can identify the acid conjugate base pairs. So for example, if we have NH4 plus as our acid, our conjugate base is NH3. So notice acid and base, number of protons. And lastly, we are left with our key takeaways from this video. So we've defined Bronsted-Lowry acids as proton donors, Bronsted-Lowry bases as proton acceptors, So we know an acid-base reaction is acid plus base, gives us conjugate base and conjugate acid. We also learned water can act like both. And it's very important that we learn the acid conjugate base and base conjugate acid pairs, because then we can predict all of our reactions. And you need to learn or memorize your strong acids and bases. Until next time.